Hi, I'm Jordan Force, and I'm with HKN, and I'm going to be solving this op-amp problem today. So, we have an ideal op-amp connected to 10 and negative 10 volt sources. We have these three voltage sources, each of them in parallel in series with a resistor. And we have these two nodes, V0, which is coming out of the op-amp, Vx, which is going to the negative terminal of the op-amp, and connected to this resistor. So to start off this problem, we're basically going to do no voltage on Vx. So we know that the current coming from VA and R1 plus the current coming from VB and R2 plus the current coming from VC and R3 is equal to the current coming out of Vx, which, since it's an ideal op-amp, none of it goes into the negative terminal, and it all goes through R4. So let's write out our node voltage equation. So, VA minus Vx over R1 plus VB minus Vx over R2 plus VC minus Vx over R3. So that's the current coming into Vx is equal to current coming out, which is simply Vx minus V naught over R4. So now we can exploit one of the properties of the op-amp. In an ideal op-amp at steady state, the voltage on the negative terminal is the same as the voltage on the positive terminal. Since the positive terminal is attached to ground, we know that Vx equals 0. And we can just substitute 0 for Vx into this equation. So we get VA over R1 plus VB over R2 plus VC over R3 is equal to negative V0 over R4. And this negative sign makes a lot of sense, since Vx, the current flows from Vx through R4 to V0, and there's a voltage drop across R4, so Vx is going to be a higher potential than V0, similar to water. So now we'll multiply both sides of this equation by negative R4, and we're going to get V naught is equal to negative R4 times VA over R1 plus VB over R2 plus VC over R3. Now, in the problem, we're given some numbers. VA is 1 volt, VB is 1.5 volts, VC is negative 4 volts, R1 is 44 kilo ohms, R2 is 27.5 kilo ohms, R3 is 80 kilo ohms, and R4 is equal to 220 kilo ohms. So we plug these numbers into this equation, and we get V0 equals negative 6 volts in this configuration. Notice that R5 does not affect the equation, the result at all. So now what we want to do is, if we assume that all the resistor values are fixed, and that VA and VC are fixed. We want to find the possible range of VB such that the op amp doesn't saturate. So when the op amp saturates, it basically means that it's trying to output a voltage that's greater than, outside of this range that's on the power rail. So let's say for Vx to be 0, for these two to have the same voltage on them, you would have to put out 12 volts. The op amp can't do that. It can only put out a voltage in the range of -10 to 10 volts. So we want to find the range for VB such that this does not happen. So we've done the no voltage stuff, and we derived this equation here. We can solve for VB now. So we know that now VB over R2, if you subtract VC over R3 and VA over R1 from both sides, VB over R2 is negative V0 over R4 minus VA over R1 minus VC over R3. So now we multiply both sides of R2 by R2 and pull out the negative. So we get VB is negative R2 V0 over R4 plus VA over R1 plus VC over R3. And then we'll plug in numbers for the minimum V0, which is negative 10 volts, and the maximum, which is 10 volts. So if V0 is 10 volts, so we're going to get VB is negative 1/2 volts, so negative half a volt when V0 equals 10 volts, and VB is 2 volts when V0 is negative 10 volts. So VB is in the range negative 1/2 to 2 volts. This is just all the real numbers from and including negative 1/2 up to 2 and including 2. This sign here just means that it's in that range, that VB is in that range. But another way, VB has to be less than or equal to 2 volts and greater than or equal to negative 1/2 volts.